The Zero Trust Reference Architecture is a structured framework essential for implementing a zero trust strategy within any organization. Its importance lies in its role as the foundational step for securing organizational data by defining and organizing network areas. Each network area within an organization, such as branch, campus, data center, and cloud, requires specific adaptations of the Zero Trust model to meet unique business vertical, functional, and regulatory demands. Understanding these elements is vital for a comprehensive security strategy.
The Zero Trust Reference Architecture embodies a comprehensive approach to network security where no entity is trusted by default from any location, irrespective of whether they are inside or outside the network perimeter. This model enforces strict identity verification, security protocols, and access controls around all resources regardless of their location. The architecture depicted breaks down into several key components and capabilities, which include policy and governance, vulnerability management, identity, enforcement, and analytics. Each of these pillars plays a vital role in ensuring robust security across the network. 1. Policy and governance. This is foundational, setting the overarching rules and parameters by which all network interactions are governed. It ensures that all data flows and endpoint interactions adhere to strict security standards, which include change control, data retention policies, and quality of service to ensure compliance and effective risk management. 2. Vulnerability management. This involves monitoring and protecting the network by continuously scanning for vulnerabilities, managing these vulnerabilities, and securing endpoint interactions. It includes technologies and processes like malware prevention and segmentation to manage risk and mitigate potential threats dynamically. 3. Identity. A cornerstone of Zero Trust, which involves verifying and managing the credentials of all users and devices attempting to access the network. It includes multi-factor authentication, MFA, and asset identity, which help in providing appropriate access controls based on the verified identity. 4. Enforcement. This is about implementing the access controls and security policies decided under policy and governance. It relies on technologies like intrusion prevention systems, IPS, and firewalls to actively block unauthorized access and segment the network as per agreed-upon security policies. 5. Analytics. Takes information across all pillars, analyzing and assessing behavior continuously to detect and respond to threats in real time. This includes traffic visibility, behavioral analytics, and threat intelligence to make informed security decisions quickly. Implementing such an architecture involves adapting these capabilities to various areas of an organization's network, be it branch locations, the main campus, data centers, or cloud-based resources, ensuring that all aspects of the network comply with the Zero Trust principles. This reference architecture not only sheds light on the detailed functioning, but also illustrates the need for an integrated approach where security mechanisms work in harmony across different domains to safeguard critical resources against both external and internal threats. This serves as a critical blueprint for organizations aiming to fortify their networks against the growing landscape of cybersecurity threats.
The Zero Trust Reference Architecture includes a high-level enclave design to support organizing critical infrastructure zones. Service area locations typically cover campus, branch, core network, WAN, and cloud, establishing a controlled flow of data traffic. These areas facilitate business applications, processes, and secure access by endpoints. Each service location is a unique segment in the architecture, ensuring tailored security measures align with business operations and connectivity demands across different organizational sections.
In the Zero Trust Reference Architecture overview, we are presented with a structured strategy for securing an organization's network by defining different zones and areas, each with a tailored security approach. This framework operates under the principle that no entity should be automatically trusted, regardless of its location relative to the network perimeter. This architecture encompasses various network and user segments, including remote users, affiliates, cloud environments, internet edges, DMZs, enterprise sectors, manufacturer sites, and corporate campuses. Each segment is detailed with 5 critical security components: identity, vulnerability, management, enforcement, analytics, and proximity, addressed at both the user layer and the proximity or environment-specific layer. By outlining these components, the architecture ensures that every zone within the organization's network has a standardized yet customizable security posture, capable of addressing unique threats and vulnerabilities inherent to that segment. Identity and vulnerability management are foundational layers that establish and assess who or what can access resources. Enforcement and analytics follow, ensuring that policies are upheld and continuously analyzed for effectiveness and compliance. Proximity captures the necessary adjustments and customizations needed for specific business environments, providing a granular level of security tailoring. By aligning security strategies with business functions and geographic or logical areas, Zero Trust Reference Architecture not only aims to mitigate internal and external threats, but also adapts to ongoing changes within each location, delivering a robust and responsive security infrastructure. This approach allows organizations to enforce and refine their security measures actively, ensuring resilience against increasingly sophisticated cyber threats. Hence, it sets a comprehensive blueprint for deploying stringent, layered security controls across an organization's entire digital and physical footprints.
Each network area presents its own set of challenges when adopting a zero-trust architecture. For instance, branches might face policy integration issues due to varying architectural standards, while campuses might struggle with threat visibility due to multiple endpoints. Recommended strategies include starting enforcement at branches for easier deployment and scaling up through lessons learned. Segmentation and policy enforcement tailored to network characteristics will enhance security and minimize risk across the organizational infrastructure. Incorporating elements of protection and risk mitigation within the Zero Trust Reference Architecture is crucial. The architecture utilizes the 5 pillars of control: identity, device, network, application, and data to fortify the security landscape. Enclave segmentation designs must prioritize risk and impact mitigation, application functionality, and regulatory compliance. By determining specific control capabilities within enclaves, organizations can effectively protect and manage critical data and infrastructure from potential threats. Branches serve as a manageable entry point for deploying zero trust principles, offering a cohesive policy implementation due to fewer endpoints and uniform functions. Communication often involves private or public links, such as MPLS or SD-WAN, for secure data transit back to centralized data centers. By integrating network access devices into the policy server and enforcing mechanisms like posture software, branches can ensure compliance and enhance security with minimal disruption during policy deployment.
The Zero Trust Reference Architecture is designed to ensure various organization sites, such as branch offices, distribution centers, and retail stores, operate securely and consistently. This unique framework underpins the principle of never trust, always verify, utilizing multiple defensive layers to prevent data breaches and unauthorized access, tailored to branch remote dynamics. Within the architecture, policy and governance are the foundation, establishing guidelines for every interaction within the network, ensuring robust change control, business continuity, and risk classification. Regulations dictate how data is handled, emphasizing quality of service, redundancy, and data retention. These policies ensure that each part of the organization responds uniformly under varied circumstances, enhancing overall security. At the user layer, identity and access management protocols such as AAAA, authentication, authorization and accounting, NAC, network access control, and posture assessments are crucial. They ensure that only authenticated and authorized entities engage with the network, dynamically adapting permissions based on continuous security assessments and predefined access protocols. Enforcement layers utilize diverse tools like DLP, data loss prevention, DNS security, and proxies to limit data exfiltration risks and ensure secure data channels. Techniques such as SOAR, security orchestration, automated response, implement automated responses to threats. Reducing the time attackers are within the network. Vulnerability management is integral, involving regular endpoint protection and malware scanning. This layer's proactive approach aids in identifying potential vulnerabilities before they can be exploited, providing an ongoing assessment and management of the threat landscape. At the analytics level, meticulous logging and monitoring of network changes, coupled with advanced behavioral analytics and threat intelligence, provide a comprehensive visibility across the network. This enhances decision-making processes, ensuring asset monitoring and protection are continuously aligned with the most current threat information. Built into every site's configuration, whether distribution or retail, the architecture ensures that the core principles of zero trust are consistently applied, assuring a robust security posture that evolves with emerging threats and changing network dynamics. This strategic uniformity across various locations bolsters the organizational defense against the sophisticated landscape of cyber threats.
Campus networks, usually larger than branches, require extensive planning for secure connectivity, owing to a diverse range of endpoints and potential threats. A definitive architecture with access, distribution, and core layers is ideal. For visibility and enforcement, initiate systems at the access layer, ensuring security appliances are strategically located. To mitigate rogue device threats, use robust visibility tools and authenticate communication between network switches with protocols like MAS-ESEC to maintain trusted and encrypted data exchange.
In a zero-trust architecture, the concept of never trust, always verify is applied thoroughly across all layers and areas of the network, from user-facing applications to the network backbone. Breaking down the architecture, we start with the policy and governance at the top layer, which encompasses a wide array of operational and security strategies, such as data governance, quality of service, risk classification, control mechanisms, segmentation, redundancy, disaster recovery, and policy retention. Diving deeper, the identity section ensures every device and user is correctly identified and authenticated using multi-factor authentication, MFA, conditional access, CA, and network access control, NAC, which are crucial for maintaining a secure and resilient network environment. This layer works in tandem with asset identity and provisioning tools to keep the identity management process streamlined and secure. The enforcement layer incorporates a series of defensive mechanisms like firewalls, intrusion prevention systems, IPS, data loss prevention, DLP, and cloud access security brokers, CISB. These tools enforce the security policies by blocking unauthorized access and preventing data breaches and are tailored to different parts of the network, such as the campus backbone and data center. Analytics play a critical role in detection and monitoring. Using tools like SIEM, security information and event management, threat intelligence, and traffic visibility analytics help in understanding and mitigating potential risks in real time. This continuous monitoring is crucial for maintaining a secure network environment. Vulnerability management processes involve regular scans, endpoint protection, and malware prevention to identify and mitigate vulnerabilities before they can be exploited. This is crucial across different network zones, such as the industrial DMZ, demilitarized zone, and enterprise segments, ensuring that all networked resources are consistently monitored and protected. Finally, each section of the network, be it the user layer, campus backbone, or data center, segments their enforcement and identity protocols slightly differently to cater to specific operational and security needs, reflecting the unique nature and requirements of each area within the network infrastructure. This segmentation helps in optimized management and security imposition, tailored to the specific characteristics and risks of each network segment.
Core networks underpin zero trust implementations, demanding stringent identity management and enforcement measures for network access devices. These devices should have dedicated management addresses for identity synchronization and support enforcement protocols, like peer-to-peer authentication. By integrating logging capabilities and traffic analysis tools, such as NetFlow, organizations can maintain oversight on communications, ensuring network access devices can securely manage data flow and policy application.
In a zero-trust security model for network architecture, each component plays a crucial role in safeguarding the infrastructure and ensuring the continuity and integrity of network operations. At the core of the system, we focus on identity management and access control mechanisms. These include IP schema, asset identity through a configuration management database, CMDB, multi-factor authentication, MFA, and privileged access management, PAM. This ensures that only authorized devices and users can interact with the network. Moving outward, the Network and Security Administration enclave is central to the oversight and management of the network. It links important administrative tasks with security operations, highlighting the integration that modern networks require. This enclave controls elements like user authentication and device configurations. Traffic through the network flows from one site backbone to another, traversing the wide area network, Quanta transport layer. Throughout this journey, different types of data exchanges and authentications occur, such as peer-to-peer, keychain authentication, and infrastructure provisioning. These processes are vital for securing data transfers and maintaining the integrity of the network communications. On the analytics side, change detection, traffic visibility, behavioral analytics, and several other monitoring activities are embedded to ensure the network performs optimally while guarding against potential threats. Tools like System Information and Event Management, SIM systems, play a pivotal role, aggregating and analyzing security alerts. These analytics support proactive measures against vulnerabilities, ensuring that network security adapts and responds to threats effectively. In essence, the network telemetry visual illustrates how various elements from basic identity attributes to complex security analytics integrate and function cohesively within a zero-trust framework. This ensures organized management, seamless security enforcement, and continuous monitoring across all network layers.
Within the WAN, zero-trust strategies encourage using overlays to protect data traffic, especially when employing external managed services. Concerns such as man-in-the-middle attacks necessitate overlay protocols, which may include dynamic VPN solutions like DMVPN or IPsec VPN for traffic encryption. Implementing a robust fabric overlay, enhanced with segmentation tags, secures data transit across managed networks, defending against unauthorized access, and maintaining consistent policy enforcement across network segments.
In the context of a zero-trust network architecture, WAN control points serve as critical junctures where security protocols can be rigorously applied to manage data flows across the network. These points link various nodes of the network, such as site backbones and WAN segments, ensuring that data transmissions across the network are both secure and efficient. The visualization highlights several key features that form the backbone of security and network management. For instance, the encrypted overlay represents a security measure where data is encrypted as it travels across the WAN, safeguarding it against potential interceptions or manipulations, commonly referred to as man-in-the-middle attacks. This strategy is particularly important in environments where the WAN is managed by an external service provider, as it minimizes the trust placed in third-party infrastructures. Another significant element is the integration of various network and security management tools within what's termed as the Network and Security Administration Enclave. This includes tools for analytics like application performance monitoring, behavioral analytics, and CM, security information and event management, systems that provide insights into the network's operation and potential security threats. Identity management components such as privileged access management, PAM, multi-factor authentication, MFA, and asset identity are also central to the architecture, ensuring that only authenticated and authorized devices and users can access the network resources. Lastly, the administration of the network is depicted as being highly centralized, with a clear delineation of roles and responsibilities that contribute to maintaining a robust security posture. The diagram instructs on the importance of having a deep contextual understanding of every element in the network, which is encapsulated in the tightly integrated provisioning and monitoring systems. Overall, the depicted WAN control points and the accompanying management tools suggest a sophisticated approach to securing a wide area network, where every piece of data and each network node is constantly scrutinized under zero trust principles, ensuring that security is never compromised.
Data centers, housing critical business assets, face risks from unauthorized devices and hidden endpoints. The virtualization trend exacerbates enforcement challenges, as traditional measures fail to track virtual server communication. Implementing a robust identity system for devices increases monitoring capabilities, while agent-based enforcement on virtual servers handles dynamic policy application. Addressing server vulnerabilities and enforcing stringent identity access controls are pivotal to protecting the data center's integrity.
The diagram demystifies the intricate architecture of a data center, underlining its pivotal role within an organization, particularly in securing, managing, and optimizing data flow. At its core, the architecture hinges on robust policy and governance measures, including but not limited to data governance, quality of service, and redundancy protocols, which are essential for maintaining operational continuity and managing risks. Within the backbone of the data center, identity and access control form the bedrock of security, employing mechanisms like authentication, authorization, and accounting, AA, multi-factor authentication, MFA, and configuration management databases, CMDB, to validate and manage the credentials of all entities accessing the data center resources. Vulnerability management is depicted as a critical component, focused on protecting endpoints, scanning for vulnerabilities, and managing databases effectively to mitigate potential breaches or data leaks. This includes implementing robust malware prevention, data loss prevention, DLP, and firewalls, as well as advanced measures like security orchestration, automation, and response, SOAR, to efficiently respond to incidents. Finally, the analytics segment emphasizes monitoring and analyzing application performance, logging changes, and detecting behavioral patterns. It employs security information and event management, CM systems, alongside other intelligence and visibility tools to ensure all activities within the data center are transparent and under scrutiny, thus supporting proactive threat identification and resolution. This comprehensive structure not only supports daily operations, but also aligns with stringent regulatory requirements that govern data management and security.
Migrating to cloud services necessitates robust security measures, including enforced contextual identities and dynamic tagging to manage access to workloads. Governance policies must outline strict asset management, lifecycle validation, and metadata definitions. Security configurations ensure proper access restrictions and extend the organization's zero trust policy into cloud environments. Continual auditing, validation, and centralized logging are vital for maintaining secure cloud operations and thwarting potential threats.
In the realm of zero trust reference architecture, which emphasizes stringent security protocols, where trust is never assumed and must be continuously verified, the depicted cloud topology is a fundamental component. This structure helps establish a secure cloud environment with multiple layers of defense, ensuring that security policies are comprehensively enforced and adapted dynamically to address potential threats and unauthorized access. At the core of this framework, you'll find centralized policy and governance mechanisms such as data governance, change control, and quality of service, QoS, which ensure that all security measures align with the organizational standards and regulatory requirements. These elements provide the foundational guidelines for how security is managed within the cloud infrastructure. The topology outlines different layers of security functions segregated into specific zones, such as proximity and cloud. Each zone addresses unique aspects of security, from identity verification, including multi-factor authentication and certification authority, to vulnerability management with tools for scanning and malware prevention. This tiered approach enables a robust strategy for preventing, detecting, and mitigating security risks effectively. Moreover, enforcement through capabilities like firewalls, intrusion prevention systems, IPS, and data loss prevention, DLP, is emphasized. These tools are crucial for maintaining secure communication channels and protecting sensitive information against external threats and internal leaks. Additionally, analytics play a vital role in this architecture, enhancing visibility through behavioral analytics and threat intelligence, which empower organizations to preemptively identify and respond to possible security incidents. This cloud topology is not only about defense, but also about maintaining efficient and secure operations across all levels of a cloud environment, ensuring that every component operates under stringent security checks without compromising on performance and service delivery. This structural approach encapsulates a vital facet of the Zero Trust model by embedding deep security into the fabric of cloud architecture, leveraging advanced technologies and strategic oversight to fortify cloud environments against evolving cybersecurity challenges.
The exploration of the Zero Trust reference architecture details its application across various service areas such as campus, branch, core network, WAN, and cloud. Each segment in the architecture supports unique or common enclaves determined by application services and endpoint interactions. Integrating protection and control elements from the 5 pillars ensures comprehensive risk mitigation. This chapter's insights underscore the importance of tailored security strategies in safeguarding organizational data and infrastructures.